A crankshaft is a shaft driven by a crank mechanism, consisting of a series of cranks and crank pins to which the connecting rods of an engine are attached. It is a mechanical part able to perform a conversion between reciprocating motion and rotational motion. The main purpose of this connecting rod is to absorb the reciprocating motion of the piston and pass it on to the crankshaft. When the crankshaft is moved by the connecting rod, it converts that movement into rotary motion and turns the flywheel, which continues to move the vehicle wheels. Without a crank, a reciprocating piston engine is not able to transmit the piston reciprocating movement to the drive shaft. In simple terms, a reciprocating engine cannot move a vehicle without a crankshaft. Various engines go through a power cycle with different numbers of crankshaft revolutions. For example, a two-stroke engine completes a power cycle after one revolution of the crankshaft, while a four-stroke engine completes a power cycle after the completion of 2 revolutions of the crankshaft. Crankshafts can be welded, semi-integrated, or one-piece. This component of the engine connects the output section of the engine to the input section. The crank acts as a link that supplies the output power in the form of rotational kinetic energy. The piston is connected to the center of the crank via a connecting rod. The crank arm allows the piston to rotate the crankshaft to generate force to move the vehicle. There are 7 key components of a crankshaft, which are crank pin, main journals, crank web, counterweights, thrust washers, oil passage and oil seals, and the last one is flywheel mounting flange. 1. Crank pin. The crank pin is a mechanical part of an engine. This allows the connecting rod to be attached very firmly to the crankshaft. The surface of the crank pin is cylindrical in order to transmit the torque to the large end of the connecting rod. These are also known as connecting rod bearings. 2. Main journals. Journals are attached to the engine block. These bearings hold the crankshaft and keep it rotating in the engine block. This bearing is, for example, a plain bearing or journal bearing. The main bearings vary from engine to engine, often according to the forces exerted by the engine. 3. Crank web. The crank web is the most essential part of the crankshaft. The crank web connects the crankshaft to the main bearing journals. 4. Counterweights. The counterweights are a type of weight that applies an opposing force that gives balance and stability to the crankshaft. These are mounted on the crank web. The reason for adding counterweights to the crankshaft is so that they can eliminate the reaction caused by the rotation. And it is very helpful to get the higher RPM and keep the engine running easily. 5. Thrust washers. At some points, 2 or more thrust washers are provided to stop the crankshaft from moving lengthways. These thrust washers assemble among the machined surfaces in the web and the crankshaft saddle. With the help of thrust washers, it can be easily maintain the gap and helps to reduce the lateral movement of the crankshaft. In many engines, these are made as part of the main bearings. Usually, older types use separate washers. 6. Oil passage and oil seals. The crankshaft oil passage passes oil from the main bearing journals to the large end journals. Usually, the hole is drilled in the crank web. When the crank pin is in an up position and combustion forces push the connecting rod down, oil can penetrate between the journal and the bearing. The crankshaft extends slightly beyond the crankcase at both ends. This will cause oil to leak from these ends. Oil seals are provided to keep oil out of these openings. There are 2 main oil seals connected at the front end and the rear end. 7. Flywheel mounting flange. In most cases, the crankshaft attaches to the flywheel through the flanges. The diameter of the crankshaft wheel end is larger than the other end. This gives a flange face to mount the flywheel. Crankshafts are typically made from high-strength materials to withstand the immense forces and stresses they encounter. There are the common materials used: carbon steel, manganese steel, nickel chromium steel, cast iron and forged steel. So, how does the crankshaft works? Basically, the crankshaft performs a simple task: translate the linear motion of the pistons into rotation. It's doing the same job as the crank arm of a bicycle, which turns the more or less up and down motion of your legs into rotation. Although the principle is simple, there are complications aplenty when it comes to high-performance engines. The combustion of fuel shoots the piston straight through the cylinder. It is the job of the crankshaft to convert this linear motion into the rotation, basically by rocking the piston back and forth in the cylinder. The terminology of a crankshaft is quite specific, so let's start by naming a few parts. A journal is the part of a shaft that rotates in a bearing. As can be seen above, there are two types of journals on a crankshaft. The main journals form the axis of rotation of the crankshaft, and the connecting rod journals are attached to the ends of the connecting rods that run up to the pistons. For additional confusion, the connecting rod journals are abbreviated as connecting rod journals and are also generally referred to as crank journals or connecting rod journals. The rod journals are connected to the main journals by webs. The distance between the center of the main bearing journal and the center of the crankshaft journal is referred to as the crank radius, also known as the crank stroke. This measurement determines the stroke range of the piston when the crankshaft rotates. This distance from top to bottom is called the stroke. The stroke of the piston is twice the crank radius. The rear end of the crankshaft extends outside the crankcase and terminates with a flywheel flange. This precision machine flange is bolted to the flywheel, the heavy mass of which helps smooth out the pulsation of the pistons at different times. The flywheel transfers the rotation to the wheels via the gearbox and the final drive. In an automatic, the crankshaft is bolted to the ring gear that carries the torque converter and transfers the drive to the automatic transmission. This is basically the power of the engine, and the energy is directed where it is needed: propellers for boats and airplanes, induction coils for generators, and to the road wheels in a vehicle. The front end of the crankshaft, sometimes called the nose, is a shaft that extends beyond the crankcase. This shaft connects to a gear that drives the valve train through a toothed belt or chain, or gear sets in high-tech applications, and a pulley that uses a drive belt to power accessories such as the alternator and water pump. Building a crankshaft involves several intricate steps, combining advanced engineering and precise manufacturing techniques. The crankshaft design is based on the engine specifications, including the number of cylinders, stroke length, and load requirements. Engineers use CAD software to create detailed designs. Typically, crankshafts are made from high-strength steel alloys, such as chromium-molybdenum steel, due to their excellent fatigue resistance and durability. A billet of steel is heated to a high temperature, around 1200 degrees Celsius, to make it malleable. The heated billet is then placed in a forging press, where it is shaped into the rough form of a crankshaft by applying immense pressure. This process aligns the grain structure of the metal, enhancing its strength. The forged crankshaft is heated and then cooled slowly to refine its grain structure. The crankshaft is heated again and then rapidly cooled, quenched, to harden it. It is then tempered to achieve the desired balance of hardness and toughness. The crankshaft undergoes rough machining to remove excess material and achieve approximate dimensions. CNC machines are used for precision machining, ensuring that all surfaces, journals, and bearing seats meet exact specifications. The journals and bearing surfaces are ground to a fine finish to ensure smooth operation and reduce friction. The crankshaft is balanced statically to ensure it remains stable when stationary. It is then dynamically balanced to ensure it operates smoothly at high speeds, reducing vibrations and wear. A surface hardening process where nitrogen is diffused into the surface of the crankshaft to increase wear resistance. The crankshaft is polished to a mirror finish to further reduce friction and improve performance. Techniques like magnetic particle inspection and ultrasonic testing are used to detect any internal or surface defects. All dimensions are checked against the design specifications to ensure accuracy. Finally, the crankshaft is assembled with other engine components, such as connecting rods and bearings, then is tested under simulated operating conditions to ensure it performs correctly. This comprehensive process ensures that the crankshaft is robust, reliable, and capable of withstanding the stresses of engine operation. Crankshafts are vital components in various mechanical systems, primarily in engines. There are some key applications in certain industrials. 1. Automotive engines. Crankshafts are essential in converting the linear motion of pistons into rotational motion, which drives the wheels on cars and trucks. Similar to cars, motorcycle engines rely on crankshafts for efficient power transmission. 2. Marine engines. Crankshafts in marine engines convert the reciprocating motion of pistons into rotational motion to propel the vessel. 3. Aerospace. Crankshafts are used in piston engine aircraft to convert piston movement into propeller rotation. 4. Industrial machinery. In power generators. Crankshafts help convert mechanical energy into electrical energy. Crankshafts in compressors convert the reciprocating motion of pistons into rotational motion, enabling the compression of gases. Crankshafts are also used in various types of pumps to convert reciprocating motion into the rotational motion needed for fluid movement. 5. Agricultural equipment. Crankshafts in agricultural machinery convert engine power into the mechanical motion required for various farming tasks. 6. Construction equipment. These machines use crankshafts to convert engine power into the necessary mechanical motion for heavy-duty tasks. 7. Small engines. Crankshafts in small engines convert the reciprocating motion of pistons into rotational motion to drive cutting blades or chains. Crankshafts are crucial for the efficient operation of these systems, ensuring smooth power transmission and reducing vibrations. The VDF 450-4 TCM Horizontal Turnmill Center by VDF Boehringer is a high-performance machine designed for efficient and precise crankshaft machining. This machine is equipped with advanced features and capabilities that make it ideal for both high-volume production and job shop environments. The VDF 450-4 TCM features a rigid machine bed and a powerful spindle, ensuring excellent stability and accuracy during machining operations. The spindle is capable of reaching high speeds, allowing for fast and efficient machining of complex crankshaft geometries. The integrated milling head provides ample power and torque for milling operations, such as cutting keyways and chamfers. The machine is equipped with an automatic tool changer, enabling quick and efficient tool changes during production runs. The VDF 450-4 is controlled by a user-friendly CNC system that simplifies programming and operation. The machine can be integrated with various automation solutions, such as robotic loading and unloading systems, to further improve productivity. The VDF 450-4 TCM's high-speed spindle and powerful milling head enable fast and efficient machining, resulting in increased productivity. The machine's robust construction and advanced CNC control ensure precise machining of complex crankshaft geometries. The machine's automation capabilities and efficient operation can help to reduce production costs. The VDF 450-4 can be used to machine a wide variety of crankshaft types and sizes, making it a versatile solution for both automotive and industrial applications. The VDF 450-4 TCM is commonly used for machining crankshafts for a variety of automotive applications, including passenger cars, trucks, and heavy-duty vehicles. The machine can also be used to machine crankshafts for industrial applications, such as pumps, compressors, and generators. Its advanced features and capabilities make it an ideal choice for manufacturers seeking to improve productivity, accuracy in their operations. Vaughan Skiwen AG is a renowned German company specializing in the production of high-quality steel products. Vaughan's commitment to quality, innovation, and customer satisfaction has made them a trusted partner in the steel industry. Their specialization is manufacturing of forged and flat steel products, large welded structures, and mechanical parts. Vaughan Skiwen offers 4 main ranges of products and services, including 1. Forged products, custom-made open-die forgings for various industries, including energy, shipbuilding, and cement. 2. Flat steel products, hot-rolled flat products tailored to customer specifications. 3. Steel constructions, large-scale welded structures for industrial applications. 4. Mechanical processing, precision machining of steel parts to meet exacting standards. 3. Vaughan Skiwen maintains a rigorous quality management system certified to DIN EN ISO 9001:2015. They also hold certifications from various classification societies such as DNVGL, LR, ABS, BV, and AD20005. These certifications ensure that their products meet the highest standards of quality and reliability. Vaughan Skiwen is famous in the production of high-quality shafts. Their manufacturing process is characterized by precision, efficiency, and a commitment to quality. There are 7 key stages of the shaft manufacturing process. 1. Raw material selection. Vaughan Skiwen sources only the finest steel alloys, ensuring that their shafts meet the highest standards of strength, durability, and corrosion resistance. The company can also accommodate specific customer requirements for materials, such as stainless steel or alloy steels with unique properties. 2. Forging. Open-die forging process involves heating the steel to a high temperature and then shaping it using a hammer or press. Open-die forging imparts superior strength and grain structure to the shaft. Vaughan Skiwen employs advanced forging techniques to achieve precise dimensions and tolerances, minimizing the need for subsequent machining. 3. Machining. Computer numerical control, CNC, machines are used to perform various machining operations, including turning, milling, drilling, and grinding. CNC technology ensures accuracy and consistency in the final product. Rigorous quality control measures are in place to verify that the machine shafts meet the specified tolerances and surface finishes. 4. Heat treatment. Depending on the desired properties, the shafts may undergo heat treatment processes to enhance their hardness, toughness, or other characteristics by annealing, quenching, and tempering methods. Heat treatment can also be used to relieve internal stresses that may have developed during manufacturing. 5. Inspection and testing. Non-destructive testing, NDT, techniques such as ultrasonic testing, magnetic particle testing, and liquid penetrant testing are employed to detect any defects or flaws in the shafts without damaging them. Precise measurements are taken to ensure that the shafts meet the required dimensions and tolerances. 6. Finishing. Depending on the application, the shafts may undergo surface finishing processes like polishing, plating, or coating to improve their appearance, corrosion resistance, or wear resistance. 7. Quality assurance. Vaughan Skiwen adheres to ISO quality standards, ensuring that their products meet the highest international quality requirements. The finished shafts undergo final inspection to ensure they meet all specifications and standards. Once approved, they are primed and prepared for delivery to the customer. By following this meticulous manufacturing process, Vaughan Skiwen AG delivers shafts that are renowned for their exceptional quality, reliability, and performance. Their commitment to precision, innovation, and customer satisfaction has made them a trusted partner in various industries. Sorel Forge, now part of Finkel Steel, is a prominent manufacturer of high-quality forged products, including alloy steels. Their strengths are custom forgings, including carbon, alloy, mold, and tool steel grades. The alloy steel production process at Sorel Forge is excellent. The process starts with a charge of solid steel scrap material from controlled sources. The scrap is melted in a 45-ton electric arc furnace. Phosphorus, an undesirable impurity, is removed during this stage. The molten steel is transferred to the ladle metallurgy furnace, LMF, for further refining. Sulfur is removed, and fluxes are added to capture impurities, ensuring high microcleanliness and toughness. Vacuum degassing, VD, reduces the levels of hydrogen, oxygen, and nitrogen in the steel, resulting in superior quality alloy steels. The refined steel is cast into ingots under argon protection to prevent contamination. Ingots can weigh up to 43 tons. Sorel Forge uses two forging presses, a 5,000-ton open-die hydraulic press and a 2,000-ton press. These presses shape the ingots into the desired forms, ensuring high internal quality and strength. They can produce forgings up to 50 feet long, round sections up to 72 inches in diameter, and discs up to 114 inches in diameter. The heat treatment facility includes gas and electric furnaces for processes such as normalizing, annealing, quenching, and tempering. Water and polymer quench tanks are used to achieve the desired mechanical properties. The machine shop is equipped with conventional and CNC lathes, boring and vertical lathes, and milling machines. They can machine pieces up to 70 inches in diameter and 40 feet long. To ensure the integrity of the alloy steel products, non-destructive testing techniques like ultrasonic testing are conducted to detect any internal defects. Magnetic particle testing method is used to identify surface cracks or discontinuities. Throughout the production process, rigorous quality control measures are implemented to ensure that the alloy steels meet the highest standards. Vaughan Skewin AG manufactures solid steel blocks through a detailed and precise process. The process begins with selecting high-quality steel scrap or raw steel materials. These materials are sourced from controlled suppliers to ensure consistency and quality. The selected raw materials are melted in an electric arc furnace. This furnace uses high-voltage electric arcs to melt the steel scrap, reaching temperatures high enough to liquefy the steel. The molten steel is transferred to a ladle metallurgy furnace for refining. Here, impurities such as sulfur and phosphorus are removed, and alloying elements are added to achieve the desired chemical composition. The refined molten steel is poured into molds to form ingots. These ingots are large, solid blocks of steel that will be further processed. The ingots are heated and forged using open-die forging presses. Vaughan Skewin operates several CNC open-die forging presses with pressing forces of 7, 20, and 30 Mn. This process shapes the steel into the desired dimensions and improves its internal structure and strength. The forged steel blocks undergo various heat treatment processes, including annealing, normalizing, and quenching and tempering. These treatments enhance the mechanical properties of the steel, such as toughness and hardness. The heat-treated steel blocks are then machined to precise specifications. This involves cutting, milling, and grinding to achieve the required dimensions and surface finish. Throughout the manufacturing process, rigorous quality control measures are implemented. This includes ultrasonic testing, dimensional inspections, and hardness testing to ensure the steel blocks meet all specifications and standards. The final steel blocks may undergo additional surface treatments, such as shot blasting and priming, to prepare them for delivery. The finished steel blocks are carefully packaged to prevent damage during transportation and are then shipped to customers. Vaughan Skewin AG's comprehensive approach ensures that each solid steel block is manufactured to the highest standards of quality and precision. Vaughan Skewin AG likely offers a wide range of steel types to cater to various customer needs. Some common types used for manufacturing solid steel blocks include 1. Carbon steel, a versatile steel with varying carbon content, offering a balance of strength, ductility, and weldability. 2. Alloy steel, contains alloying elements, e.g., chromium, nickel, molybdenum, to enhance specific properties like strength, hardness, corrosion resistance, or heat resistance. 3. Stainless steel, known for its corrosion resistance, often used in applications exposed to harsh environments. 4. Tool steel, high carbon or alloy steels with excellent wear resistance and hardness, suitable for tools and cutting equipment. The specific steel type is chosen based on factors such as strength, hardness, ductility, corrosion resistance, the intended use of the steel block, customer specifications. Vaughan Skewin AG likely employs rigorous quality control measures throughout the manufacturing process to ensure consistent product quality. Incoming steel ingots are carefully inspected for defects, chemical composition, and conformance to standards. Key process parameters like temperature, pressure, and cooling rates are monitored and controlled to maintain consistency. The finished blocks are measured to ensure they meet the specified dimensions and tolerances. Tests like tensile strength, hardness, and impact resistance are conducted to verify the steel's mechanical properties. Techniques like ultrasonic testing, magnetic particle testing, and radiographic inspection may be used to detect internal defects without damaging the block. A final visual inspection is often performed to check for surface defects or imperfections. The manufacturing process of carbon steel overpacks for high-level radioactive waste is carried out under extremely advanced technology and strict quality control. The purpose is to manufacture safe and reliable containers that can maintain the containment function of radioactive materials for a long period of time. Carbon steel materials that meet the characteristics required for long-term stabilization of high-level radioactive waste are selected. The selected materials are procured under strict quality control and undergo thorough inspection. The shape, thickness, structure of the overpack are designed in detail, taking into consideration the shape and type of waste, the disposal environment, etc. The drawings required for manufacturing are created based on the design drawings. Steel plates are cut, bent, welded, etc. into the specified shape based on the design drawings. Welding requires high airtightness and strength, so it is performed using advanced technology such as automatic welding robots. Non-destructive testing is carried out at each process to check for defects. Inspection of welded joints is particularly important, and internal defects are examined in detail using X-ray inspections, etc. The processed parts are assembled to complete the shape of the overpack. After assembly, non-destructive testing is conducted again to check the quality. The interior and exterior surfaces of the overpack are subjected to surface treatment to improve corrosion resistance. The type of surface treatment varies depending on the disposal environment and the material of the overpack. A final inspection is conducted on the completed overpack to ensure that it meets all requirements. Inspection items include dimensions, shape, airtightness, strength, radiation shielding performance. Overpacks that pass the inspection are securely packed and transported in special transport containers. Strict management is also performed during transportation to prevent radiation leakage.